Okay, good morning. Welcome back to class. Last class we finished the one question related to the angular momentum equations. So here we have additional questions also associated with the angular momentum equations. And the topic we would like to predict the power delivered by the French turbines. So, what the French says turbines? So, here is a video to illustrate what is the French turbine. So, I would like to play the video, and you will see what's the turbine.
Welcome to the video tutorials of Mechanismuller. This animation authored by Dr. Seyhan Ersoy is the property of the client GDF Suez and subject to copyright limitations. We thank GDF Suez for giving us the permission to publish this video. There are three major types of water turbines. The Pelton turbine requires large water head and low flow rate, and the Kaplan turbines require low water head but large flow rate. The Pelton turbines usually build in mountainous regions, while the Kaplan turbines are located in lowlands. These restrictions make these two-kind turbines less common than the Francis turbine. The Francis turbine fills a large gap between the Pelton and Kaplan and it is widely used. They operate in water head from 10 to 600 meters, and primarily used for electric power generation. Their power output can be calculated from the water head and flow rate and typically range from 10 to more than 700 megawatts. One of the distinct advantages of the Francis turbine with respect to other water turbine is that they can also be used as water pump. This makes them ideal for the pump storage systems. This animation shows the operation of a Francis turbine in a dam. The arrows show the water path and direction inside the dam. The water from reservoir behind the dam transferred to the turbine by a penstock. The penstock diameter of a Francis turbine could be as large as 10 meters. The water coming from the penstock is transferred to the inlet scroll, which distributes the water equally around the wicket gates. Water passes through the wicket gates, which controls the amount of water passing through the turbine, before reaching to the runner. This in effect controls the power output of the dam. Wicket gates also adjust the angle of the water reaching to the runner. After passing through the wicket gates, the water reaches to the runner. The water pressure forces the runner to rotate. The rotation speed of the runner can be in the range of 80 to 1000 revolution per minute. The water continues its motion downward under the runner to the exit pipe. The exit pipe discharges the water to the environment as low-pressure water. The turbine shaft of the Francis turbines is almost always mounted vertically. This makes discharge of the water much easier due to swirling effect of the water, in the inlet scroll, and the effect of the gravity. The rotation motion of the runner is transferred to an electric generator shown in here. The generated electricity is converted to high voltage current and transferred to the grid to be consumed. One big advantage of the water turbines is that power output can be regulated very easily. If the demand is reduced, the amount of water flowing to the turbine can be reduced relatively short period of time. We thank our client GDF Suez giving us the permission to publish this video.
Okay, so the movie just showed the idea how works of a Francis turbine to generate the power. Okay, so we go back to see our questions. So here is the map views of the Francis turbine, and the idea is water directed by the guide fans into the rotating runners of the turbine, And the guide fence has 70 angles from the radial directions. So you can see we have the water flowing here, and this is the our water flow directions, and we have the angle in here. Okay, and because here is the 70 degree in here, so right here we just another intersect angle is the 20 degree here, and then the water is with the only a radial component velocity with respect to the environment. The outer diameter is the 1 meter, and the inner is 0.5 meter. So that indicates this is the outer, and the inner is in here. So this is 1 meter, and here is 0.5 meter. Okay, and the distance across the runner is the 4 centimeters here. So where is the 4 centimeters is the width in here is the 4 centimeter. Okay, so and actually we know that the discharge in this problem is the 0.5 meter cubic per second. Okay, and the rotational rate of the runner is the 1200 radian per minute. So we first convert the RPM to the radians per second. So we know that the 1200 and the radius, one circle is equal to pi radius, right? And per minute change to the second. 1 minute is 60 seconds. Okay, so we can first compute the radius in angular speed by calculator. So the answer is around 62.8 radians per second. Okay, and then the power density of the water density is the 1000 kilogram per meter cubic. So, but the question is required we to answer find the power produced by the turbine. So how can we compute the power? So here you can see the equations some highlighting here. So the P is the power and the T is the moment, and the omega is the angular speed as we show in here. So that's the formula summarized here. If we have the moment and multiply the angular speed, and then we can calculate how large power generated by the turbine. So the key knowledge in here, we first need to calculate the moment for our questions. So based on the angular momentum equation, we know that the sum of the moment will equal to the m rate outflow part, the R related to the outflow cross the flow out velocity, right? And minus the inflow, the mass flow rate, and the R in flow the distance arms cross the inflow velocity. And for these problems, we can see where is our inflow. The inflow is in these directions, and the outflow is pass through with the center of the runners. So it's a pass through the center point, so there is no distance arm. So in our question, actually we don't have the contributions moment by the outflow. So in this question, we only have m rad ri distance cross the velocity in. Okay, so we need to consider each element items showing here. So we first consider how we know the mass flow rate. So since we have the low and we have the Q, so we can compute the mass flow very quickly. So we use my calculator to check the mass flow rate will equal to the 500 kilogram per second, right? And then we know that the Q discharge is equal to the velocity in factor dot product with the area factor, right? So we go back to see the here. What are the V in? V in is the directions for these directions, and then the area. Where is the area? The area is the dashed line regions. And what are the dashed line regions? The dashed line regions is equal to the cross-section area in here. So the area in the yellow colored is the radius of the circle multiplied the thickness 4 centimeters. Okay, and then here we dot product, so we need to project the force is parallel to the normal factor of the cross-section area. Okay, so here we need to find out the V in velocity magnitude, and we do the sine 20 degree to project the velocity flow directions and project the cross-section area, multiply cross-section area. So we don't know the V in magnitude, and we have the sine 20 degree, and the cross-section area is the radius. So I compute the area in here is the radius of the outer circle. So the pi outer circle, the diameter is the 1 meter. So this is the radius length and circle length, and multiply the 0.04 meter. Okay, it is the width of the runner. So use my calculator to check the answer. Multiply 0.04. So that will equal to the area is 0.1256 meter square. So we can multiply the answer in here 0.1256. Okay, so we can we actually know the discharge. So it's equal to the discharge divided the sine 20 degree and divided the 0.1256 meter. Okay, so in that case we can calculate how large of the velocity in. So the discharge is 0.5 divided the total area, cross-section area, divided the sine 20. So that's equal to the 11.63, and this is the velocity, so the meter per second. Okay, so we can go back to see our formula in here. We have a mass flow rate. So the mass flow rate, and where is the R1? And we need to take into account the Ri cross product with the velocity in. So I erase here and we need to project the velocity into the these directions, and we have a radius distance along the casserole center and with these directions. So the R is these directions, and this is our originally our velocity is these directions, and we need to project to the tangent the directions, and R curls the V, project V, so it's a minus moment. So here we have an additional minus, and the Ri cross product with the velocity. So here the velocity in need to multiply the cosine 20 degree. Okay, so we put a number inside here. So we know that the mass flow rate is 500 kilogram per second, and the R is the outer radius is the 1 meter, and the velocity is 1.63 meter per second, and multiply the cosine 20. So we can calculate the final moment that we have. So I use the calculator to double check the answer. It's equal to the 5 and 465.93. The unit is Newton multiplied meter. So finally we would like to calculate the power generated by the turbine is sum of the moment multiplied the angular speed. Okay, we have the angular speed in here already. So we have the power here. So we multiply two values together. So I directly use the calculator to check the answer. So I write down the final answer calculated from the calculator. The 34360.5. Okay, that's the unit is the watt. And so that will equal to the 343 kW will contribute by this Francis turbine. Okay, so that's a very typical problems. We already know the angular speed of the runner, and we know that the velocity with the angle have the angle with the radial directions of the fans is 70 degree. So we can base on the angular momentum equations to first calculate the how large moment we have, and based on the equation shown here, we have the moment multiply the angular speed will equal to the power. So we can predict how large power generated by the Francis turbine. This is the efficient problems of the turbine. Okay, so according to we have know the idea knowledge of the momentum equations, and so next semester we have the fluid mechanics and laboratory experiment related to the fluid jet. So that's the problem related to the fluid jet. And the fluid jet, the device can help us to better understand how momentum changes and associated with the force we have. Okay, and you can compare the theoretically force and observed force, the difference between them, and then you can calculate how large energy loss we have in practical case. Okay, so that's why I just showed a table summarize. So the idea is quite simple. We will have the a velocity outside in here, so we will have the velocity u, and then the fluid jet of the velocity will impact the plate here. So there is a receiver plate, and the plate will have some connect to the force recorder. So we can have the force recorder will provide how large mass we have in this question in this experiment. Okay, so the idea we can measure the how large mass we have in here. Okay, so we can convert the mass to the force. So this is the observed force we have. And for this question, we can adjust the discharge we have. So we can adjust the discharge first. So we can have the discharge and use the clock to measure how large time we have related to the discharge changes. So we can compute how large discharge we have. And because we have the discharge, and we know that the discharge divided the cross-section area, and then we will have the initial velocity associated with the fluid jet. And we based on the Bernoulli equation shown here, so we can predict how about the fluid jet related to the U0, and the R is the distance between the jet and the plate. So we can predict the U0, and then we can compute the momentum changes by the log Q U0, and then this is related to the external force. So we have the external force magnitude. So actually the laboratory experiments, the idea is we would like to compare the theoretically force and there is a measured force. And we try to understand how large discrepancy is between the measures and the theoretical force. Okay, the difference will be associated with the energy loss for this laboratory experiment. Okay, so the next semester we have the several laboratory experiments, and then we can remind you how theoretical and the fluid mechanics ideas can be applied to the real case. Okay, so the next one, I would like to introduce a little bit about the differential form of the momentum equations. So before that, I need to interpret the continuity and the equations, and then it's the differential form of the continuity equation. So we start from the idea I have teach before. There is the continuity equation, right? And then the proof scheme, and the idea is we only focus on this fluid qubit, right? That indicate we only focus on the problem for a small qubit of the fluid. Okay, so and this is a quite smaller volume, and we know that the volume is equal to the delta x, delta y, delta z. Is a quite smaller volume, delta x and delta y, and we have the delta z. Okay, so and we can compute the MCV, the mass in the control volumes. And finally, we can derive the equation shown on the bottom. This is the differential form of the continuity equation. So that indicates we have a density in here, and if the density changes with the time plus the divergence of the low v, v is the velocity factor indicated to the UVW, the different velocity directions to combine into together to be the vector velocity. Okay, so the idea is we have the steady flow. So we know that if the steady flow, so the density didn't change with the time, right? And if we know that the flow is in compressible flow, so that indicates the density didn't change with the spatial changes. So we know that we can simplify the continuity equation to be only have the divergence of the velocity vectors will equal to 0. Okay, that's just I just reminded you how the formulas related to the differential form of the continuity. So now we can move to the differential form of the momentum equations. And the final formula we will call that is the Nivea-Stoke equation. So it's a very quite important equations in the fluid mechanics. So you need to know how and what is the Nivea-Stoke equation. Okay, so the idea is quite simple. We just start from the momentum equations. We know that the external force will equal to the dt and integrate along the control volumes with the low v dv, and plus the integrations of along the control surface is low v and the capital V dot product with the cross-section area factor. Okay, so first we only consider the cross-sections along the x directions. Okay, so that's we can simplify the equation only along the x directions, and we still have the same formula on the right hand side items. So I think in this slide we first focus on how about the external force in our problems. And since I already mentioned, because we discussed with the differential formulas in here, so we only consider a small cubic fluid. So right now this is our small cubic fluid. And the cartoon figure showing the left hand side, we just describe how many force we have include the problems. So the first we have the force here related to the body force. So we have the body force in here. If we have some accelerations like the gravity, so we have the body force contributed by the acceleration. And we have an additional force we need to take into account for the pressure force, right? And only one significant difference compared with the previous ideas. In this part, we consider include the viscosity effect. So we will have the viscous force. And the viscous force is kind of the shear force related to the fluid particle. Okay, so totally we have the body force first, and we have the pressure force, and we have the final shear force. So the first one, what is the body force? Okay, so I just summarize. We have the body force, and plus the pressure force, and plus the final force contributed by the shear force. So first, the body force will related to if we have the density, and the density multiplied the volume is a delta x, delta y, and delta z. So we have the mass related to the fluid qubit, and we only consider we have the accelerations along the x directions. So the fx is the acceleration along the x directions. So we have the fb. So how about the pressure force in here? So that we need to take into account the pressure force for the two cross-section areas. So we in that problem we can assume the center pressure is the P0. So we can apply the Tidal expansions idea to expand the pressure on the right hand side and the pressure on the left hand side. Okay, so we can predict the pressure on right hand face and the left hand cross-section area. So that indicate, and we notice that the directions of the pressure force is go to left, and here is go to right. So we first use the tidal expansions. We know that the pressure at the left hand is a P0, and the minus we assume is a linear changes along the x directions. So the minus dp dx multiply 2 over delta x. So this is the pressures on the left hand side, and need to minus the pressure on the right hand side. So the pressure on the right hand side is plus, and dp dx, and multiply 2 over delta x. And we need to, this is only the pressure difference balance, and then we need to multiply the cross-section area for here. So here the cross-section area is equal to dy and dz. Okay, so we can balance the formula shown here. So it will equal to the P0, and the P0 will cancel out. So we only have the gradient, pressure gradient item in here. So that will equal to the minus dp dx, and we have additional delta x here, and then multiply the outside is the dy and dz. Okay, so we have the this is our the force related to the pressure force. And we go back to see the viscosity force in here. So we know that the how many force will have the x directions. So I highlight in here, this is 1 and 2 and 3. And they use the tau to indicate the shear stress. And as we know, we can see the shear stress will have the two index, like the tau xy. What are the meanings? The first y in here is that indicate the shear stress is acting on the plane with the normal factor along the y directions. So that is a normal factor of the shear stress, and the x is the force directions. It's a force direction. The direction is along the x directions. Okay, and then if we focus on the tau x, and what is the force along the tau x, so again we can consider the tau x, the center pressure shear stress is tau 0. In the right hand side, the tau x on the right hand side, we need to predict based on the tau x 0. So it's equal to the tau x 0 plus the tau x along the x directions is linear, and here we have a 2 over delta x, because the right hand side the force directions go to right. So here is the positive, and minus the left hand side tau x 0 minus the d tau x x and the dx and 2 over delta x. This is the shear stress, and we also need to multiply the cross-section area is along the delta x, delta y, and then multiply the delta z. So this is have the delta y and then multiply the delta z. Okay, so this is related to the d x tau x dx, and then multiply the delta x, delta y, and delta z. So this is only contribute the from the shear stress along the x component. And we need to consider all of the different components, but the force shear stress direction is along the x. The next one is the tau y x0, and also plus the d tau y x, and here is along the y directions. Okay, and multiply 2 over delta y, and minus the tau y x0 minus the d tau y x dy, and multiply 2 over delta y. And the outside the area is this plane. So this plane is equal to the delta x multiplied delta z. So here is the d tau y x and dy multiply the delta y, delta x, and delta z. So we only still have the final shear stress is related to the tau z x and 0. So we plus the d tau z x. Sorry, I correct it. So the tau z x, and the directions, the changes is we along the z directions, and 2 over delta z, and minus the tau z x0 minus the d tau z x divided the z, and multiply 2 over delta z, and the area in here is equal to the phase in here in this plane. So it's equal to the delta y multiply the delta x. Okay, so that the final is equal to d tau z x, and the dz will equal to the delta d multiply delta y multiply delta x. So we can compare all of the items showing here. We all of the first item include the delta v. Okay, so in our final summarizing here, we just take the delta v outside, and the inside we only have the body force, right? So first we have the body force along the x directions in here, and we have the pressure force related to the x directions, so in here. And the most important thing, the pressure force in here is the minus, so you can see the minus sign in here. And we have 3 items associated with the shear stress, and so this will equal to the d tau x, d tau y x, and d tau z x. Okay, so we just combine all of the items together in here. So the slide just summarize all the force contributed by the shear stress, and the body force, and the pressure force. Okay, so the next one we deal the problem with the right items. So the right items, what do we have? We have the and dt, and we integrate along the control surface, and we have a low u dv, right? And plus the along the control surface, and the low u, what the uu is the velocity along the x directions, and we have the velocity factor dot with the cross-section area. So I use the divergent series. I would like to convert the integration problem along the area to be the volume. Okay, so you can compare each other and try to apply the divergence theory in our original formula in here. So the first item I didn't change because it's already integrated along the volumes. Okay, and so I just changed the second items to be the volumes, but the volumes right now, the inside item to be the divergence. Okay, so it's a divergence of the low u v factors and d. There's no dot for dot, just integrate along the volume, right? Okay, and we go back to see our problems, because our problem already consider a very small fluid qubit, so we don't need the integration operator in our momentum equations. So we just remove the integration items, and we have the low u, and multiply the delta x, delta y, and delta z. This is the dv, and plus the divergence of the low uv vectors, and multiply delta x, delta y, and delta z. So we compare with the previous slide, both equation we have the delta x, delta y, delta z here, and here we also have the delta x, delta y, delta z here. So the momentum equations for the small qubit fluid particle will rearrange to be the body force minus the dp and dx, and plus the d tau xx dx, plus the d tau yx dy, and plus the d tau zx and dz will equal to the d low u dt, okay, and plus the divergence of the low u v factor. Okay, so the next step, we would like to only focus the item on the right hand side here. So we first focus the item on the right hand side. So we expand the right hand side item is equal to the d low dt, and multiply the velocity u, and plus the low, but it's du and the dt, right? And we expand the differential factors. Here is the d and dx with the I directions, plus the d and dy with the z directions, and plus the d and dz, the k directions. Okay, and multiply the low u I directions, plus the low u v z directions, plus the low u w k direction. Okay, so it's equal to d low dt u plus the low du dt, and here we only have the item I, j, and kk, so it's equal to d dx, and the inside the low u is from the II directions, and the d and dy, and inside we have a low uv, and the plus the d and dz, and the inside we have a low uw, right? So we expand the differential items in here again. So what do we have? We have the first we have the and we have the d and du dx. Okay, multiply the u plus the low u but the du dx. Okay, and the plus again the d and dx. But here we have the low v. Okay, multiply the u and the plus the low v and the du. Sorry, here is the dy, and the low v and the du dy, and the plus the d and the low w dz, multiply the u and the plus the low w and the du dz. Okay, so we just take a look. We combine all of the items related to the u, and u. So I can combine all of the items related to the u. Wait, it has some. So u. Okay. So I take the u outside and combine all items related to the u with d low dt, and the plus the d low u dx, and the plus the d low v dy, and the plus the d low w dz. Okay, and if either other items is equal to a low du dt, and the plus the low u du dx plus the low v du dy plus the low w du dz. Okay, so the question in here, if you take a look, the item shown here, that will equal to the similar items related to the differential form of the continuity equation, right? The continuity equation is equal to d low dt plus the divergence of the low v factor, right? And based on the continuity differential form, we know that actually equal to the 0. So finally, what we only have, we don't have the item on the left hand side. So we only have the low du dt plus the low u du dx, and the plus the low v du dy, and the plus the low w du dz. So as the final formula showing here. Okay, and because of the time limit, so today I may stop here, and right now I would like to highlight the pipe quiz questions in our next week. Okay, so I can tell you the next week we only have the one questions for the pipe quiz, and the question will related to the rocket behavior predictions. So we need to go back to see the problems for the rocket equation showing here. So that's the for the model the rocket behavior, we need to apply the momentum equation, and we need to decide the the reference frame because our problem is under accelerating. Okay, so we first start from the momentum equations, and we find out our external force and what the momentum flow, net momentum flow. So you need to know what the problem and the significant formulas to predict the rocket behavior, and that you need to know how can we derive the equation, the final equations related to the rocket behavior. Okay, so 就是说下周的这个考试你要知道，我们只有一个问题，然后这个问题是跟火箭的这个行为的预测有关系。那你要知道怎么去推导这些火箭的这个最后的这个预测的这个公式，就是你最后的终极速度跟质量流率，还有这个thrust force， 还有这个n 就是 final rocket 的质量跟 initial 的这个质量的比值，是可以去预测最后的这个燃烧殆尽的速度的。那就只有一题，所以希望大家可以好好准备。Okay, so today I start here and see you next week.